All right.
Okay.
Go ahead.
I can,
Go ahead.
yeah. So for our first OTTER Talk of 2023, we got Priyadarshi Dey from the University of South Florida. We'll be talking about a class of bi-contractive projections on Banach spaces. And there's some other fun parts of the title, but
yeah,
I'll let you take it from here.
Okay. All right. Thank you. Thank you, Merrick. Actually, thanks all of you for inviting me, for giving me a talk. I have been following OTTER for I don't know for how many months, but yeah, I'm here around. I try to attend some of the meetings, but I sometimes cannot. But it's a great initiative, I believe, for people like us who are starting their career or who are in the grad program. And yeah, that's a great thing to do. All right, so I'm going to talk about a class of bi-contractive projections on Banach spaces. And as I so in the abstract, so I mentioned a couple of things. I'm going to so a part of the title was something old, something new, something borrowed, and something blue. So I'm going to talk about something old. That means something which have been done already. I'll also try to mention something new as well, if time permits. So we'll see, because I would like to give a lot of introductions and a lot of fundamentals of what's coming. And also, I would also like to use some of the already existing results to incorporate what we have done so far and what our plans are. So with that being said, so this talk, I would like to divide the talk into 3 parts. The first part, I would like to give a little bit of introduction about projections. However, we know what projections are. Projections are so powerful and things like that. But still, I would like to introduce a little bit about projections and how I'm going to use projections in this talk. The second part actually deals with a special class of operators. They are called Hermitian operators. And I'm going to give you a little bit of introduction to the Hermitian operator part as well. However, this talk is not mainly focused on Hermitian operators. So I'll probably not go over a lot of stuff on Hermitian operators, but I definitely am going to give you an introduction. But the most interesting part of this talk is when I combine those 2 operators, which are projections as well as Hermitian. So I call it a Hermitian projection. So I call it a Hermitian projection. So I actually am interested in all those operators which are Hermitian operators as well as our projections. So I call them Hermitian projections. And although I haven't defined what a bi-contractive projection is yet, but I'm definitely going to do that. And we are going to see that these Hermitian projections, they are indeed bi-contractive projections on Banach spaces. And that's what I'm going to talk about. So the first question that comes here to our mind is, hey, there are so many operators to study. Why would you like to study projections? So why are projections important? So here's, so there's a catch. Why are projections important? So all the importance, at least to me, are centered via the Banach space and analysis. I'm pretty sure there are lots of applications of projections in different fields, different disciplines, but all the importance that I'm going to talk about, they are all more or less based on analysis, or mostly functional analysis. Okay. So for the first thing that I would like to tell you is projections are operators with a very simple spectral structure, because we love operators which have simple spectral structure. What does it mean? It just means that the spectrum is actually indeed inside 0 and 1. You can prove it by using the spectral mapping theorem. Excuse me. And it is really interesting, and it can also be shown that if on top of that, if P is an orthogonal projection, which means that if P square equal to P as well as P star, then the spectrum is exactly equal to 0, 1. So the spectral structure is very simple, and any operator which has a very simple spectral structure is actually very easier to understand. Okay, that's the first thing. The second thing is the most important one, which I love and which I actually explored very recently. So for many classical Banach spaces, the projections actually generate B of X. And what is B of X? B of X is the standard set of all bounded linear operators from X to X. X is a Banach space and T is bounded. So this is bounded. So what it means is, so given any bounded operator, so it just means that there are some Banach spaces where if you take any bounded linear operators, of course it's linear for me, you can write that linear operator, that bounded linear operator as a linear combinations of projections. And this study was started long back in 1950s. And one of the most interesting results was due to Matsumoto. I don't remember which year was it, around I think 1970s. He proved a phenomenal result that every bounded operator on a Hilbert space is a real linear combination of at most 10 self-adjoint projections. That's according to me, it's phenomenal, because you take any bounded operator on a Hilbert space, you can write it as a linear combinations of at most 10 projections. So projections could be less, but it is at most 10. And historically saying, the number 10 is the best improvement that has been made so far. The first result along those lines was by, I forgot his name, but it was early 1950s. He proved that any operator, any bounded operator on a Hilbert space is a linear combination of 257 self-adjoint projections. So from 257, then it boiled down to 64, and the latest one is actually proved by Matsumoto. It's actually 10 self-adjoint projections. So it is really important. So the idea is, if we understand projections, so we would be able to understand many bounded operators on Hilbert space. So that's actually really a powerful statement.
So Day, is it known that 10 is sharp, or is it
up to now? I don't. Yeah, I think it is sharp. I think it is sharp. Yeah. And people have tried to make it. I think Matsumoto, he didn't prove that it is the sharpest one, but people weren't able to prove anything smaller than that up until now, as far as I know.
Another question. So
yeah.
When you say projection, like I will often think of like a metric projection, but this isn't linear, so I should not think about this, right?
Yeah.
Okay.
Yeah. So all the projections, yeah, that's a good point. All the projections that I'm going to talk about in my talk, they are all linear. Okay, most of them are linear and also bounded. I don't deal with unbounded projections. And once again, the self-adjoint projection just means that it's P star equal to P as well as P square. So this property is always there. It's always there. And another result that I would like to mention, just out of curiosity, it was once again another Japanese mathematician, Nakamura. He did for finite dimensions. So he proved that for T in MNC, where MNC is our standard MNC, this can be expressed as a linear combination of at most 8 projections. So this is for at most 8. So as Chris was mentioning, but this number is sharp, but this is only true for finite dimension. So any operators on finite dimensions for M and C in specific, people are able to prove that this is a combination of 8 projections. But in general, for infinite dimensional Hilbert space, it could be separable, it could be non-separable. The sharpest bound that I know, and I believe that that's actually the 10. All right, so these are 2 important reasons. The third reason is, I think most of us know that spectral theorem. So spectral theorem also gives us an idea of how important projections could be. So there are many versions of spectral theorem, but I would like to restrict myself onto the compact, normal, and compact operators. So what it says is, if K is compact and probably normal operator on Hilbert space, by B of H, I once again mean that this is a bounded operator on Hilbert space, then we know that this operator can be written as the weighted sum of projections, where this lambda n Pn, where n is some index set. And what are lambda n's? Since T is compact, actually what I mean is T is in B of H, okay? So these lambda n's are these are non-zero eigenvalues. Since T is compact, so we have eigenvalues in the spectrum, and these Pn's are projections onto the eigenspaces. This is the nth projection. This is the nth projection onto this eigenspace. Okay, so that's also interesting. And what do I mean by that? That might be a question. What do I mean by equality? By equality, I mean that they converge in norm, so in operator norm. So this is T minus n belongs to I, this lambda I, Pn, this actually goes to 0 in operator norm. That's what I mean. That's what this equality actually means. I would say this is not K, this should be T. Okay, so you see, once again, so if you have to study compact normal operators, self-adjoint operators on Hilbert spaces, since they can be written as the weighted sum of projection. Are there any questions?
I have a question, but so real combination of projections is self-adjoint always, right?
Say that one more time. I couldn't hear you very well.
Sorry. No, I'm saying that real combination of self-adjoint always, right?
Yeah.
I'm referring to this theorem of Matsumoto. So
yeah.
Every operator is not self-adjoint, though.
What is the real combination of projections is a self-adjoint? Is that what you're trying to say?
Yeah. But then every operator will be self-adjoint in this way.
No. Okay. So let me see if I understood your question. So you're saying that T is sum over alpha I pi, I equals 1 to n, and pi is a projection. That's what this theorem says.
Yes, and I.
No, I don't think I still understood your question. Can you repeat that again? Sorry.
Maybe I'm understanding. You're saying that every operator is a linear combination of self-adjoint projections. Why doesn't that imply that every operator is self-adjoint? Yes. Does that seem somewhat like what you were asking?
Oh, no, but yeah, every operator you can write it as a sum of 2 self-adjoint, right? T1 and T2. But here they are not a real linear combination, because this is I times T2. That's a different thing. So every operator you can write it as a sum of 2 self-adjoints. So T1, T2 are self-adjoints in this way. But what it's saying is every operator is I mean, these may not be projections. So T1, T2 may not be projections, but here they are saying that every operator is a real linear sum of projections. That's what they're saying. And here also, this T1 and T2, they are self-adjoint, but they may not be projections. So yeah, so that's not very obvious. Does that answer your question? Maybe we can talk a little more about it after at the end of the talk. Okay, if I understood your question, probably I'll understand your question better. But anyway, so so here is the thing. So these are very three main important reasons. There is one more which I would like to tell you is the following. But so one reason people really study projections, or it has been very famous in Banach space theory at least, is because of the complemented subspace problem. So there have been a lot of work done, complemented subspace problem. So it has been a very, very interesting problem all throughout in Banach space theory to understand that so given any Banach space X, what are the complemented subspaces of that Banach space X? For example, this is the question. So which closed subspaces of a Banach space are complemented? So this is a very important question that was around for a long time. It's not solved there yet, but there have been examples for which you have a complemented subspace, and there are examples where you do not have complemented subspaces. So, and why is it so important? Why is projections related to it? Because of the following reasons. Because projections actually are very, very closely related to the complemented subspaces. Why? Because of this.
So Dave, do you mind just telling us what you mean by complemented?
Yeah, that's exactly what I'm going to define. Yeah,
Thank you.
that's exactly what I'm going to define. So what are complemented subspaces? So we said that a subspace Y of X, let's say X is a Banach space, is complemented if we can say that this is closed subspace. Okay, it's complemented if there exists a projection or bounded linear, of course. So for me, it's bounded linear, such that this subspace is a range of that projection. Okay, so the range of any bounded linear projection is going to be a complemented subspace. So understanding the projections from one space onto a subspace of that is really important while you try to classify the complemented subspaces of a Banach space. And there have been many examples, don't have on top of my head, but it can be shown that the subspace, the complemented subspaces of capital LP. It has also been shown that little LP has no complemented subspace. C0 is not complemented in L infinity. So there have been many results along that. But the important part is, if you understand projections, you will be better at understanding the complemented subspaces of a Banach space. Okay. So here are some of the interesting aspects of studying projections. Although there are many, but I'm not going to talk a lot about that.
Sorry,
but,
Dave, can I just ask a quick question? So you said big LP and then little LP, but you can witness little LP as a big LP just on counting measure, right? If you're talking about over the naturals or the integers, do you need like a finite measure space or something like this?
Okay. Actually, so what I mean is the following. Probably I did not say it correct. Thanks for pointing that out. What I mean is for LP, for little LP, P not equal to 2, P bigger than 1, has non-complemented subspace. Okay, so it does not have any complemented subspace. I mean, it has so non-complemented subspace. What it means is there exists a subspace which is not complemented for LP. Okay, but for capital LP, there are complemented subspaces. For capital LP, for P between 1 and infinity, it has been classified that the complemented subspaces are the following. Complemented subspaces are the following. This is a complemented subspace. This is a complemented subspace, all of it, etc. That's what I mean. Okay, that's what I mean. And also, this is an interesting result in Banach space theory that C0 is non-complemented in L infinity. It is non-complemented in L infinity. So, so the relation that you're talking about, I mean, it still holds. Of course, LP, if you take the counting measure, this is little LP. But what it's saying that for little LP, we have found some non-complemented subspaces. But for capital LP, we don't know yet. But only the known complemented subspaces are some of this. That's what I mean.
Yeah, thank you.
Okay, and so the mostly the projections that I'm interested in, or at least for this talk, this is, I would like to put it as a definition. So there are two types of projections that I'm most interested in. One is a contractive projection, and the another one is a bi-contractive projection. So let me define what they are. So the contractive projections, a projection P is called contractive if the norm of P is equal to 1. So that's what I mean. And it's called bi-contractive if norm of P is equal to 1, as well as the complemented projection also has norm 1. Okay, so if P is norm 1. And remember that if P is a projection, I minus P is always a projection. And projection is, and also these are some facts. So if P is a projection, then that would imply I minus P is also a projection. And it is also true that the norm of any projection is always bigger or equal to 1. And so contractive means that the norm is equal to 1, and bi-contractive means if both the norms are equal to 1 or not. But in this talk, what I am mostly interested in, the projections which are bi-contractive. So, and that's what I'm going to define next. Okay. I'm not going into very details on some other aspects of projection, because there are some very, very interesting problems on Banach space theory which deals with projections, but let's not talk more about that. So the second part is about Hermitian operators. So Hermitian operators. So I'm going to define all of it very formally, but it's just, let me tell you where it is coming from. So Hermitian operators are a natural generalization to the self-adjoint operators on Hilbert spaces. So recall that, I'm sure we all know this definition. So an operator T from H to H is self-adjoint. H is a Hilbert space here. It is self-adjoint if we have the norm, the inner product of this is equal to this inner product, and which is true for every xy in H. But the problem in generalizing it to general Banach spaces is we all know that not every Banach spaces have inner products. So the question is, how would you define a Hermitian operator like, or maybe a self-adjoint operator like operators in general in Banach spaces? And so that's why it is a sort of generalization to self-adjoint operators on Hilbert spaces into a Banach space setting. I'm just going to give you the formal definition in a couple of minutes, but this is a general idea of what Hermitian operators are going to look like. And as I told you before, I'll also give you some examples for sure. And as I told you before, the main focus of this talk would be to combine projections as well as Hermitian operators, and we are going to call them the Hermitian projections. Okay. So let me define that. And as you'll see very soon, that this definition depends heavily on the structure of isometries on Banach spaces. So what is an isometry? So the isometry is a linear operator. A linear operator T from X to X is an isometry if the norm of Tx equals norm of X. And for sure, isometries need not be linear. but the isometries that I'm going to consider in today's talk, they are all linear. Okay. And it is true by Mazur-Ulam theorem that any isometries is actually a real linear. Okay, real linear. But anyway, our isometries are linear. So definition of Hermitian operators. Definition of Hermitian operators, and as I told you before, this definition is based on the structure of isometries on the Banach spaces. Okay. So let's say X is a Banach space. So this BS means Banach space. Okay. So T in Bx is called a Hermitian operator. If this operator e to the I t t is an isometry. And this has to be true for every little t in R. Okay. And to be honest, let's try to understand what is this operator, what this operator is indeed. What is this e to the I t t? I am pretty sure that you may have guessed before that this operator is nothing but an infinite, it's like a power series equals 0 to infinity I t t to the n over n factorial acting on X. And in order to prove that it's an isometry, we would always prove that this norm is equal to norm of X for every t in R. Okay, so we say that T is a Hermitian operator if this series of equality is actually true. Okay, and it is clear that this is an operator. This ITT is an operator from X to X. Okay. All right. So and also interestingly enough, which I'm not going to do here, but it can be shown that this if you go to Hilbert space setting, and you can actually prove that for Hilbert space setting, this actually turns out to be an isometry. You can actually prove that just by considering this inner product. You can actually prove that this turns out to be X comma X. So it's actually, this definition is really consistent with what we already know for Hilbert space setting. Okay, so it's just a sort of generalization. Okay, time for an example, maybe. Let's see. And I always prefer giving the simplest examples. And here it is. So I'm just going to give you a trivial Hermitian operators. However, there are many examples that can be given, but this one is the trivial one. So let's say X is a Banach space, and for a real scalar lambda, the map T, which goes from X to X, which is given by a scalar multiple of identity, which is a scalar multiple of identity, turns out to be a Hermitian operator. And this is very important that this scalar has to be a real number. It may not be true if the scalar is a complex number. So if you have a real number, any operator which looks like this, which is the scalar multiple of identity, is indeed a Hermitian operator. And it has a name. It is called a trivial Hermitian operators. Yeah? Hermitian operators. And so the question is, it is true that given any Banach space X, you'll always have a trivial Hermitian operator. So in every Banach spaces, there is at least the trivial ones that you can find. But the question is, which is more interesting, at least to me, is the following. So there are some spaces where the Hermitian operators are only trivial. That's actually a little more interesting. So I'm going to make a list of spaces where the only Hermitian operator are trivial ones. Once again, every Banach space has trivial Hermitian operators, irrespective of any Banach space. But what is more interesting here is there are some Banach spaces where the only Hermitian operators are the trivial one. So I'm going to give you a couple of examples. The first one is, these all examples were proven in 1970s by Bergson and Sarur. The first one is our well-known C101, which is the set of all continuously differentiable functions. So f is continuously differentiable function. And as you can see that when we talk about the Hermitian operator or not, norm plays a very important role. So we have to mention the norm as well. And the norm here is given by, it is a combination, is a sum of the infinite norm and the sum of the infinite norm of the derivative. Okay, it can be shown that the proofs are not very trivial. You have to go through it needs a lot of work, at least a decent amount of work to show this, but it is indeed true, and I think the result is actually pretty interesting. There are a few more, but I'm pretty sure that this space would make all of you very excited, is the Hardy space on the unit disk. The Hardy space on the unit disk is one another space for p between 1 and infinity, for p not equal to 2, for obvious reason, also has trivial Hermitian operators. So the only Hermitian operators that you have here are trivial Hermitian operators. Okay.
So Dey, is this first example you mentioned, is this not true if you just use the soup norm?
It is not true. Yeah, it is not true. Yeah, for soup norm, it is not true. That's a great point. For soup norm, it is not true, but under this norm, it is actually true. But for Hardy space, you just use the regular Hardy norm that we know. That thing.
Thanks.
All right. There are a couple more, but let's not talk more about that. But let us go into the third part. I have a question before. How long do I have? Is it until 1 or?
Aim for about till 12:50.
12:50. Okay.
You can go over obviously if you want, but
all right. Okay, I'll see. Okay, thank you. All right, so here is the thing. So the third part and the final part of the talk, which is the most interesting, at least to me, is to talk about Hermitian's operators, which are as well as projections. And this is what we called Hermitian projection. So this is what we're going to talk about for the rest of the talk today. Before I do that, I would like to introduce one class of projections which are very interesting, and actually which has a very close connection to Hermitian projections. And let's not make mysteries here, but which turns out to be the equivalent to Hermitian projections. That is known as, let me define first. So the definition is that's called a bicircular projection. I'll tell you why this name, but this is called a bicircular projection. And it turns out that we'll see very soon that bicircular projections are indeed equivalent to Hermitian projections. We'll see that a little later today. So what is a bicircular projection? Of course, I would like to mention that it's very new in terms of its development. It was done by Stacko and Zalar. They were both engineers, actually, mechanical engineers. I think they were from Hungary, somewhere Europe. So they actually came up with this definition. So let's say X is a complex Banach space. And I don't know much about it, but I remember that last time Anirban talked about Reinhardt domain, and I was reading their paper, and they mentioned that they were working something with Reinhardt domains, and that's exactly when they came up with, they felt the need of such type of projections. But I'm sorry, I'm not an expert, so I can't tell you more about this. So let's say X is a complex Banach space, so P be a projection. So P is called a bicircular projection. Bicircular projection. And from now on, I would probably abbreviate it BCP. I always tell my students that I'm so lazy, so I always try to find shorthands. So I call it BCP, okay? So it's a BCP if this linear combination is actually an isometry. If this linear combination is an isometry. And what is alpha and beta? Alpha and beta are any number, any real number. Okay. So this is a special class of projections. And why? I'm just going to prove next that this is one class of bi-contractive projections on Banach spaces. So there might be many class of bi-contractive projections on Banach spaces, but this is one of them, and this is one of my interests in terms of research. So first of all, what does it mean? It just means that if you act it on an X, if you act it on an element X, and if you take the norm, you are going to get a norm of X for every X in X. Okay, that's what it means. And this thing actually is very symmetric. So instead of talking about this, we can always do something like that. So we can just pull out e to the I alpha, and then we can write it as e to the I beta minus alpha times I minus P of X. This is equal to norm of X. This has to be true, but since alpha is real, so this is norm 1 or absolute value 1, however you call it. So it's nothing but we can just write it as negative IT I minus P, where T is just a real number. T is just a real number. So since it's symmetric, so this definition is actually equivalent to saying this thing as well. So from now on, just to simplify our work, we can just do it like that. Okay, we can use this definition. All right, here comes the most important thing. Two properties of this type of projections. The first one is so every bi-contractive projections, every bicircular projection is indeed bi-contractive. So let's take a bi-contractive. Let's take a proof of that. It's very simple. Could probably be an exercise for my linear algebra students, but it's very simple. So let's look at the norm of P. So what is the norm of P? So assume that, so let P is a bicircular projection. So let P be a bicircular projection. So what would be norm of P? So can I write this norm as 1/2 of 2P minus I plus 1/2 of I? Of course we can. That's just a simple math. And you can see that this is smaller or equal to 1/2 times the norm of this plus the norm of this. And you can see that this is actually norm 1. Why? Because we know that P is a bicircular projection. That just means that P plus, or maybe you can use this definition. That just means that e to the I alpha P plus e to the I beta I minus P is an isometry. For every alpha beta, correct? Now I can take alpha to be 0 and beta to be pi. That would give you that this operator is indeed an isometry. So this is isometry, so this norm is equal to 1. So that is equal to 1/2 plus 1/2. That's equal to 1. So norm of P is smaller than or equal to 1. So norm of P is smaller or equal to 1. All right, but that's not it. We need to prove that the complementary projection, which is I minus P, that will also have norms less or equal to 1. And the proof is more or less similar. So you just write it as 2I minus 2P, and which I can write it as 1/2 I minus 2P minus I. And now I use the triangle inequality, which is this, plus 1/2 times 2P minus I. And by the same logic, it is actually equal to 1. So in other words, norm of P is smaller than 1, or actually equal to 1. And norm of I minus P is also equal to 1. So therefore, this projection is indeed a bicircular projection. So bi-contractive projection. So every bicircular projection is a bi-contractive projection. So from now on, having a similarity with the title, So this is the type of projections that I'm interested in on Banach spaces. Yeah, on Banach spaces. And a quick observation along those lines, which I'm not going to prove, very easy to see, that if P is a bicircular projection, that is if and only if the complementary projection is also bicircular. Okay? That's actually easy because this definition is so symmetric. If you change your P with I minus P, nothing actually changes. So that's an interesting thing. So now, what was later found out in late 2007 is even more interesting. So this was due to James Jamison in 2007. He actually proved a very, very interesting thing that, hey, these bicircular projections are indeed Hermitian projections. These are just the Hermitian projections on Banach spaces. And recall the definition of Hermitian projection. So if an operator is called an Hermitian projection if it is Hermitian as well as projection. Okay. So what I'm going to,
sorry, just to go back, and this I was just about to ask about the Hilbert space setting. Bicircular seems like it should be equivalent to orthogonal.
Oh yeah, that's a great point. You actually saved my I actually saved my time. I was about to say that. That's a great point. That one of the greatest example would be in the orthogonal projections on Hilbert spaces. Orthogonal projections on Hilbert spaces. Thanks, Chris. Orthogonal projections on Hilbert spaces is definitely a bicircular projection. Bicircular projection. Okay.
Thanks.
That's one of the well-known examples. There are many more, but this is the most natural and the well-known example. All right, so let's get back to this this thing. So let's say let P be a projection on X. Then the following are equivalent. Okay. What are they? So number one, P is a Hermitian projection on X is same as saying that P is a bicircular projection on X. So these two are actually these Hermitian projections and bicircular projections. They were being developed independently, but it turns out by this beautiful theorem, and I like the proof because it's very short. It's actually cute. Okay, I call them cute proofs. So this is extremely beautiful proof, a couple of lines, and it turns out that they are actually equivalent class of projections. So let's see. Excuse me. Let's see how we prove this. The proof. So there are two things to prove. One, if and only if two, but a series of equality would prove everything. Okay, so let's try to do that. So remember that Hermitian operator. So P is, so let's look at this operator first. Let's look at this operator, e to the it P. Let's look at this operator. Okay. So this operator, I'm actually ignoring the X. It is actually acting on X, but I'm just ignoring that. So this is 0 to infinity ITP to the power n over n factorial. But remember that since, okay, let me write one extra step. So if we expand this, we get I plus ITP plus IT square over factorial 2 P square. But remember that P is a projection. Okay, so P is a projection. So all powers of P, so P to the n is just P for every n. Since P is a projection, so P to the n is P. So all of them are P indeed. Okay, so I can write it as, I can pull out I, and then I can write this as IT plus IT square over factorial 2 plus IT cubed over factorial 3. It goes on like that. And you can write it like this. And by our knowledge of calc 2, this is nothing but a series e to the it minus identity acting on P. And now what I would like to write it as, I can pull out an e to the it from the entire expression. I can write it as e to the negative it identity plus P minus e to the negative it of p as well. And now this is e to the it. You can combine them to write p plus e to the negative it times I minus p. So this operator on the left looks something like this. And let's act it on x. Let's not be lazy. Okay. So now we have to prove one if and only if two. So let's take the norm. So if I take the norm on both the sides, we all can see that this has absolute value 1. So it turns out to be p plus e to the negative it I minus p acting on x. Now here's the thing. So let's try to prove 1 implies 2. So one says that P is a Hermitian projection. That just means that this operator on the left is an isometry. So that should be the case. That should be P plus e to the it I minus p acting on x. And that actually proves that this operator is an isometry, and this is true for all x. So that implies P is a BCP. That's one implies 2. Okay. One implies that P is a Hermitian projection. So this operator right here is an isometry. And that's why I use this. And that actually proves that the operator on the right is an isometry. So how about 2 implies 1? It's the same thing. So 2 implies 1. 2 says that P is a bicircular projection. So this operator is an isometry, which proves that this is equal to norm of x. So that implies that e to the itp x is equal to norm of x. That implies 1. That actually implies 1. Okay. So they are equivalent. They are actually equivalent. So this, from now on, whenever we talk about Hermitian projections, they are nothing but the bicircular projections for us. So one natural question, since it is really cute. I mean, I wish I will have a proof like that in my life. It's so strong and intense, but it's really easy. So one natural problem to talk about, which I don't have enough time, and I'll probably not be able to show the proof. But one natural problem in this area of research is the following. So given a Banach space X to describe the structure of its bicircular projection or Hermitian projection, whatever you call it, because they are the same. Now, what do I mean by describe? Describe just means that give me a description of those operators. Can you give me description of that operator? So given any Banach space X, so the main line of work is the following. So you just start with the Banach space. You try to give a description of such operators. Okay, and that's going to be one of the important problems for us. And this has been well known for classical Banach spaces. For example, it has been well known for CK, E. It has been where CK, E is the vector valued continuous function from K to E. It's also known for B of H, which is indeed a C-star algebra. And it's also known for LP of omega. Okay, so what they have done is so any operator. So they, for example, if I talk about CKE, the problem is to classify all such operators which goes from CK of E to CK of E, which are bicircular projection, and they actually give you a form. Let's say P of F equals maybe something like that. Okay, so that's the main problem. That's the main problem that people work with. But we actually proved a very interesting theorem along those lines. We actually took the Banach space of bounded operators from X to Y. Okay, so what is the problem with this space? This is not a regular space because people have done things for algebras, but B of X comma Y is not even an algebra. So B of X comma Y just means that set of all bounded linear operators from X to Y. T is bounded linear. And this is not even an algebra because that joint doesn't belong. You are not always allowed to compose. The composition doesn't make sense all the time. So it's not an algebra. So we did not actually follow the line of proof that people were doing. So we came up with a little different sort of proof for it, but since I do not have time, and unfortunately I wouldn't be able to give you an idea of the proof this time, but I can tell you the result that we have proved so far. Okay, and we have seen that in order to classify the Hermitian projections, we need to know the underlying structure of isometries on those spaces. Okay, but if you think carefully that in general for two Banach spaces, we may not know the structure of their isometries, so we had to reduce it down to a very classical situation, a very particular situation, and that's exactly what I'm going to give you the theorem. So the theorem that we proved, and me and some of my colleagues, so let XY, some of my collaborators, I would say, be an ideal pair. And what is an ideal pair? I'll just give you an idea in a minute, such that X is not isometric to Y star. And what happens if X is isometric to Y star? The result is not very interesting. So that's why I'm omitting the case. And let's say we have a bicircular projection from P of X comma Y. This is a projection, then P is a Hermitian projection if it has the following form. Hermitian projection. If and only if there are two possibilities. Either P has this form, and where Q is a bicircular projection on X. And number two, the another possibility would be P of A equal to R of A, where R is another Hermitian projection on Y. So if you know the underlying structure of Hermitian projections on X and Y, you could definitely do this problem for B of X comma Y, and that's what we did. But we did it for specific pair of Banach spaces. They are called ideal pairs. There are 4 conditions, are some little bit more intense in the sense that they both have to be reflexive. They have to be strictly convex, approximation property and things like that. But I'm not going very deep into that. But ideal pairs, for example, a pair of our interest would be LP comma LQ. Such a pair is actually an ideal pair. Okay. So yeah, so we did solve the problem, but for a specific class of Banach spaces, and this is what actually I would like to end my talk today. Thank you so much.